Hello, this is Professor Kuehn. We've been talking about Chapter 5 of A Student's Guide to the Great Physics texts, where Galileo is discussing the relationship between pendular motion and harmony. Specifically, we were talking about the case of a vibrating string. And Galileo was discussing how if one has a vibrating string, I'm going to simplify this somewhat. So let's suppose you have 2 points that the string is stretched between. And I'll make the string right here. And this is a vibrating string. You pluck it and it vibrates back and forth. It has some natural frequency at which it vibrates. And this natural frequency, we'll call that F0. That's the natural frequency. And the natural frequency gives rise to the pitch of the note that one perceives. And that natural frequency depends on 3 variables. So the first thing that it depends upon is the length of the string, L. The second thing that it depends upon is the mass per unit length of the string, mu. That's the mass per length. And that can be adjusted by either making a thicker string or by making a string of some more dense material like gold instead of hair. And the third thing that it depends upon is the tension that you're keeping the string under. So if, for instance, you had a string with a pulley suspended and a weight suspended, that weight would produce a tension. I'm omitting that here and just talking about the tension. This is the force under which the string is being pulled. Okay, and last time we mentioned that this natural frequency, I'll call it F0, depends in a particular way on those variables. It goes inversely as the length. That is, as you make the length longer, the frequency gets smaller. It gets to be a lower note. It also depends on the tension under the square root of the tension, and it also depends on the mass per unit length, and that goes in the denominator. This means that if you increase the tension, the frequency is going to get higher. You might think about a guitar string, the frets, if you turn it to increase the tension, the pitch is going to go to a higher pitch, a higher frequency. If you have the mass per unit length get larger, the frequency is going to get lower. You might think about on a guitar, the thicker strings, the ones with the larger mass per unit length, are the lower notes. And one way you might think about this is that a string with a larger mass per unit length has more inertia, it's heavier, so as it's swinging back and forth, it's harder to turn it around, so as a result, it's going to be vibrating more slowly. Now, how did we get to this formula? Well, we actually arrive at it empirically using Galileo's data. He mentions that if you have 2 strings, so let's draw 2 strings. This is string 1, and this is string 2. And let's enumerate the length of string 1, the tension of string 1, and the mass per unit length of string 1, and length of string 2, tension for string 2, and mass per unit length of string 2. And what we could do is think about how do the frequencies of string 1 compare to the frequency of string 2? How are those related to one another? Well, Galileo says that if L2 is equal to twice L1, then the frequency of string 2 is going to be 1/2 of the frequency of string 1. Actually, he says it the other way. If L1 is 1/2 of L2, then F1 is twice F2. Okay, so this is, as you make the string longer, you have to double the length in order to go down by an octave. Okay, and you can see right away that that is captured by this formula right here. If we wanted to know the frequency of string 2, let's just do this example, compared to the frequency of string 1, well, that would be the tension of string 2 divided by the length of string 2 divided by the square root of the mass per unit length of string 2. And string 1, there's a tension of string 1 divided by the length of string 1 times the mass per unit length of string 1. And let's go ahead and imagine that tension remains the same and the mass per unit length remains the same and just the length varies. So if the tensions are the same, then these are equal to each other, they cancel out. If the mass per unit length is the same, these two cancel out, and you're left with the ratio of L1 over L2 because this is in the denominator of the denominator and so on. And so if we specify that L2 is twice L1, we'll put the twice L1 for L2, and L1 remains the same right here. Cancel these out, and you get 1/2. And in other words, F2 is equal to 1/2 of F1, which is exactly what we anticipated. Okay? So that makes sense. The frequency should go inversely as the length. What about his next data point? He says if, for example, the tension 2 is equal to 4 times tension of 1, all else remain the same. All else the same. What would be the ratio of the frequencies? Well, once again, let's use this formula and see if we find, as he says, then the frequency of string 2 should be twice the frequency of string 1. That is, it will go up by an octave if you quadruple the tension. Does this work using this formula? Well, let's find the ratio F2 to F1. Again, T2 over L2 mu 2 and T1 over L1 mu 1. Okay, and we're keeping the mass per unit length the same, so those two are equal, so they cancel out. The lengths, let's suppose we keep the same, those two cancel, and we're left with the square root of T2 over T1. And if T2 is 4 times T1, like this, then we cancel the T1s, and we get F2 over F1 is equal to the square root of 4, which is 2, or in other words, frequency 2 is 2 times frequency 1, and this is exactly what we wanted here. In other words, once again, this dependence on the tension gives us the correct relationship between tensions and frequencies. Okay, so this would be maybe data point 1, this would be data point 2, and over here we can probably fit data point 3. Let's do that. Let's drag this stuff over here, and let's move this. Okay, data point 3, he says, if the mass per unit length of wire 2 is equal to 1/4 the mass per unit length of wire 1, all else the same, he says then you will have the frequency of 2 equal to twice the frequency of 1. In other words, by quartering the mass, you go up by an octave. Does this work? Well, let's do it once again. Let's find the ratio F2 to F1, T2 over L2 root mu 2, and T1 over L1 root mu 1. And if the tensions are the same, the lengths are the same, we are left with the square root of mu 1 over the square root of mu 2, because these were, remember, in the denominator of the denominator, so it comes to the numerator. And mu 2 is 1/4 mu 1, so mu 1 and 1/4 mu 1. Mu 1's cancel, you get the square root of 4 right here, which is equal to 2. In other words, once again, if I can fit it in here, F2 is equal to, 2 times F1, which is exactly what we wanted. So in other words, this formula right here captures all of the data that Galileo presents us with. So once again, summarizing, if we have a vibrating string, the pitch of that string depends on the vibration frequency, and the vibration frequency depends on the tension it's held under, the length, and the mass per unit length. And Galileo has been exploring this and explaining how this all fits together. I should say right away that guitars, of course, as you know, are not the only instruments. You have organ pipes and flutes and things like that. And those, likewise, the pitch is going to depend on the frequency, but the frequency is going to be adjusted in slightly different ways. Okay, I'll talk to you next time.